Alright. 2.6 chain rule for derivatives. Fun.
I'm not
And at the
spontaneous
halfway
person.
point.
So even the jokes are scripted?
You'll never know. And you're thinking, was that scripted? We're going to talk about the chain rule today. Chain rule, oh man, it's so cool. It lets you tie all this calculus stuff together. This is the last major rule that we have. We will talk about implicit differentiation, which leads us to related rates, something very useful for you. But as far as the rules go, this is it. This is the last derivative rule that you get. Other than that, it's pretty much just applications.
Nice.
So that's kind of nice, right? So basically the rules are
Product,
rule,
quotient,
quotient rule, chain rule. Most of your calculus rests on that. Most of your derivative rests on those rules. So what this is, what the chain rule does, it gives gives you a way to do derivatives with compositions. So it lets you take derivatives by using compositions.
Compositions. Okay. Got it.
And just to refresh your memory on why we might do this, I'll give you that example again. It's on the last video, so I want to make sure it's on this one as well. This is the reason why we want to learn the chain rule. I gave you this to you earlier. I said, can you take the derivative of that thing? Easily.
Easy.
In fact, if I did this,
6x. Period.
derivative would be 6x, and then you're done, right? And I built on it a little bit. I said, okay, well, what if it's not that? What if it is squared? Could you still take the
Foil
derivative? That's just
Or
it. You probably
product
foil
rule.
that out, right? Distribute it, and then take it turn by turn. I said, okay, well, what happens if it's cubed, and you go like so the same
Foil
thing,
it.
or use the product rule. I could still do that. Distribute one of them, use product rule. But as soon as we get to things like this, and I think this is where I went the oh crap, right? You go, come on, man, are you serious? Do we really have to do that? Yeah. But if you think you're going to distribute this 100 times, I mean, that's just a waste of time. So there's got to be a better way to do derivatives of this. And as a matter of fact, there is, and it's actually not hard. It's kind of an easy way to do it, and you're going to like this. So all the times where you had to distribute, remember like when you had this squared, you had to distribute that, right? Like in the first set of homework, you're like, oh man, this is tedious. We'll end the tedium. Now this takes care of that. So anytime you can see a composition, I'm going to show you the composition here in a second. You can use the chain rule. So I come with theme music now. All right. The question
Bass
is,
music.
can I express this thing as a composition? Which is why I had you cover compositions and had you go the reverse of compositions, looking for a function within a function. That's why we did that. So when we get to this point, like, oh yeah, I kind of understand that idea now. So can I express this as a composition? And the answer is, yeah, I can. And here's how you do it. Here's a pretty basic way to do these things. What you're going to do, you're going to cover up the inside of your function. So what I mean by the inside here is the 3x squared minus 4. You with me on that? You're going to cover that up, and you're going to go, okay, I'm going to make a function y equal to whatever you covered up becomes an x. And you know what? Let's make it a u. A u to the 100th. Make it a u to the 100th.
Okay.
Do you see how I got that? Do you see that by holding this part out, I get a function that's very basic. Y equals u to the 100th.
Move
Do you see
100
where
in
u to the
front.
100th is coming from? But then you have another function to
99.
express. You now need to say, okay, well, u is going to be, what did you cover up?
3x squared minus 4.
Then that has to be your u. And that would be a very basic composition. Do you see if I put the u in for this u, this expression in for this u, I'm going to get that back again? Can you see the composition here? Basically, if you cover it up, you go, okay, that's u to the 100th, and u is what's under my hand. And that's how we get those two things. Raise your hand if you feel okay with that so far. So sure, this is a composition. That's not bad at all. Well, could you find dy du? Could you find that?
Let me try it. Well, it's as simple as just going 100 u99, right? And then you plug in u again, or substitute it for 3x squared minus 4. 99 like that. And I don't know if we mess with that 100 at all. I don't know. Let's see.
What's this mean to do? Derivative of y with respect to
you.
what?
U.
Oh, with you. Okay, so do it. What's the derivative with respect to u? That should be a very easy one for us.
199.
100u to the 99th.
You okay with that so far? You sure? Okay. Could you find du dx? Could you find du dx? That's the derivative of u with respect to x.
Oh, okay. There's more to it. Du dx. Six x.
How much is that going to be? That's the 6x. Are you okay with these two things so far? So we write this as a composition. We take the derivative of the first expression, that's the overlying function. We take the derivative of the inside expression, that's what we chose as our composition to compose into that. But the problem is this. What we ultimately want to find is dy dx, right? We don't have that yet. We have dy du, we have du dx, but you're going to find out right now why we stick with this notation, because this is kind of cool. Are you ready for it? If we want to get dy dx, so what about dy dx? What about dy dx? The question is, can we put these two things together in such a way that it will equal dy dx? For instance, I'm looking at a dy du, and I'm looking at a du dx. Do you notice how the du here is on the denominator, and the du here is on the numerator, and we have a dy on the numerator, which we want, and a dx on the denominator, which we want? What operation can I put between this one and this one so the du's will be gone and I get dy dx?
Product rule, so that the du's cancel out.
Yeah. You know what? Look at this. If I say, well, let's just take dy du.
Oh, just multiplication.
That looks like an 8, doesn't it?
Is it just multiplication?
Let's multiply it by du dx. The beauty of this notation is that those little pieces do act like something you can cross out, something you can simplify. So what happens to the du's in this case? They're gone. This right here is the chain rule. What it says is that dy dx will be equal to dy du times du dx. This is chain rule. That's the chain rule. Okay, so how do we use it in practice? Let's apply it to this scenario, okay? So when I ask you for d dx of 3x squared minus 4 to the 100th power, who cares where you got that from? Can you do the derivative? Here's what it says. It says take your dy du take your dy du, that's this. Okay, I'll switch it that way. Take your dy du times your du dx. In our case, that's the derivative with respect to u of u to the 100th. That's where we got this, right? Derivative with respect to u of u to the 100th. Are you seeing where that's coming from? Then it says times the derivative of the inside, the 3x squared minus 4. That's the du dx. Times your du dx. In our case, that's the derivative with respect to u of u to the 100. That's where we got this, right? Derivative with respect to u of u to the 100. Are you seeing where that's coming from? Then it says times the derivative of the inside, the 3x squared minus 4. That's the du dx. Do you see that dy du is this thing? It's the derivative of your function with respect to u. That's what this part is. Are you okay with that?
Yep. This would be
dx, that's the derivative of what you call u. The derivative of what you call u is the inside part. If we take that derivative, it says multiply dy du times du dx.
What do you have to use product rule?
So take the derivative of the overlying function, multiplied by the derivative of the inside function. That's what this says to do. What was this again?
Or no, oh yeah, because you just,
Times, what was
you
that?
know the derivative of both.
Do you see a problem with this? Yeah, we have x's and we have u's. We want which one? We want x's. Do you know how much u is equal to? Sure, that's why you had this over here. So if we can do that substitution, we go, okay, the x looks great to me, but the u doesn't look so great. I want to make that u back into what u equals. So let's do that. We'll get 100, 3x squared minus 4, because that's our u, to what power? Don't forget about the 99th power. Don't forget the exponent. Times 6x. Now, you could make it a little bit prettier, but I want to come back to this and talk about this for a second, okay? Because I want you to see the practicality of the chain rule. Firstly, what are you going to do with this?
Distribute?
You're going to do something with this. What are you going to do with the 6x? Multiply by what number?
100.
Yeah, do that. Okay, don't leave it hanging out there as a times 6x at the end. Now, naturally, please don't do this. Don't distribute the 100.
Okay.
Okay, you can't do that.
I didn't
because
think
that's
you could.
exponent. That says in order to distribute
And
the
they started
100,
pointing at
you
it.
have
I'm
to
like, wait,
FOIL
what?
that out 99 times. Do you get it? Please, for heaven's sakes, don't do that. 99 times. Because that's exponent. That says in order to distribute the 100, you'd have to FOIL that out 99 times. Do you get it? Please, for heaven's sakes, don't do that. All right, don't do that. Just multiply this number times this number. And we get 600x. X squared minus 4 all to the 99th power. That's it. That's a pretty easy way to do a derivative, isn't it? Not too bad. Now let's look at what actually happens here. Because I want you to see this. This is going to be in general what we did. Is there a way that you can get from here to at least, well, actually probably this step. We can get almost from here to here in one step without showing a u, without showing a du.
Move the 100 out in front. Subtract by 99, or subtract by 1. Where's the 6x come from again? Take the derivative of the inside term, polynomial, and multiply it with your leading coefficient.
U dx and a dy du. Without showing that stuff, I want you to think about what we're doing. Do you see what happens to the 100? What happens to the 100?
Moves out in front.
Yeah, that's basically just your power rule. Do you see it? The 100 comes down to the front. You leave this thing alone, right? That's in the parentheses. It says you leave it alone. Why do you leave it alone? Because you end up substituting back in the u. That's why, because with the composition, you're going to get that u back again. Do you see that? You're going to have some u here. You're going to get that. So we have a u back again. That means you don't change it inside. Where's this piece come from? Where's this back again? Do you see that? You're going to have, it says you leave it alone. Why do you leave it alone? Because you end up substituting back in the u. That's why, because with the composition, you're going to get that u back again. Do you see that? You're going to have some u here. You're going to get that. So we have a u back again. That means you don't change it inside. Where's this piece come from? Where's the 6x come from?
Derivative of the inside polynomial.
And this is called the general power rule. It's a corollary of the chain rule. The chain rule is the overarching idea, but what we can do oftentimes with this is something called the general power rule. And it says the power rule works in general if you do this. And I'm going to show it to you right now. So general power rule. So when you ask me, well, wait, I thought you said there's only 3 rules. There really are. There's only the product rule, the quotient rule, and the chain rule. However, the general power rule is like a little piece of the chain rule, okay? You get the general power rule from the chain rule. Do you understand? So the general power rule says, what if you need to take a derivative of some function to some power?
Haven't we already seen this?
Well, if you
moved down in
need to
front.
take the derivative of
It's
some
across the
function to some power. Here's how you do it. This is called the chain rule. And here's how you do the chain rule. I can show it to you if you really want.
Or wait, but then it would be the... Then you have to find the derivative of the inside, multiply it by the
Two.
outside maybe.
This is what would happen. You'd say, okay, what's my function? You'd say y equals u to the n. True? Where u would equal f of x. Do you believe me? You follow still? That's what the chain rule would say. Well, this says, okay, if I took the derivative of u to the n, remember your power rule? Power rule says you bring down the exponent, you subtract 1 from it. True? This would say, okay, dy du would equal n u to the n minus 1. Follow me so far? Du dx would be the derivative of f of x. That's, oh, how do I want to write it? I'll just say this. The derivative of f of x. You could write f prime of x. You could write that as well. Are you guys okay that the derivative of u to the n is n u to the n minus 1, and the derivative of f of x is the derivative of f of x? Does that make sense to you? I'm writing this way so we have a formula in just a second. Do you see the chain rule at work? We have dy du, we have du dx. So in order does this come from? So when you ask me, well, wait, I thought you said there's only 3 rules. There really are. There's only the product rule, the quotient rule, and the chain rule. However, the general power rule is like a little piece of the chain rule, okay? You get the general power rule from the chain rule. Do you understand? So the general power rule says, what if you need to take a derivative of some function to some power? What if you need to take the derivative of some function to some power? Here's how you do it. This is called the chain rule. And here's how you do the chain rule. I can show it to you if you really want me to. This is what would happen. You'd say, okay, what's my function? You'd say y equals u to the n. True? Where u would equal f of x. Do you believe me? You follow still? That's what the chain rule would say. Well, this says, okay, if I took the derivative of u to the n,
U equals f of x, y equals u to the n.
remember your power rule? Power rule says you bring down the exponent, you subtract 1 from it. True? This would say, okay, dy du would equal n u to the n minus 1.
Yeah, okay.
Follow me so
Sure.
far? Du dx would be the derivative of f of x. That's, oh, how do I want to write it? I'll just say this. The derivative of f of x. You could write f prime of x. You could write that as well. Are you guys okay that the derivative of u to the n is n u to the n minus 1, and the derivative of f of x is the derivative of f of x? Does that make sense to you? I'll write it this way so we have a formula in just a second. Do you see the chain rule at work? We have dy du, we have du dx. So in order to find dy dx, we'll have dy du times du dx. Well, what that says is do a substitution.
So the derivative of the function with respect to x equals the derivative of the function with respect to u, with u being f of x, and the derivative of u with respect to x, which is the derivative of x. I think I already said how this is gonna go, but it's kind of weird looking at it without numbers, McCullough. But you could like plug this in.
N u to the n minus 1 times the derivative of your function.
Yeah, okay, so exactly what I said. The exponent moves to the front. The original exponent that you took from is subtracted by 1. And the whole expression is multiplied by the derivative of f of x.
From the inside. How much is u? What's u equal to? Because we did that composition. What was u in our case? So do that substitution back into there.
Or 6x.
And what you end up getting is n f of x to the n minus 1 d dx of f of x.
And this works because if you do it, I guess, the right way, let's see. You're basically doing dy du times du dx. The du's cancel out. That gives you dy over dx. And yeah, if you use that logic, then use dy du, which is on the right, it's the derivative of u to the 100th times the derivative of 3x squared minus 4, which is 100 times u to the 99 times 6x. Multiply 6x by 100, and yeah, it's easy.
Now, did we say anything about f of x at all? Did we make any qualifications about f of x? So then this should work in general, right? Anytime we have a function raised to some power, we could use the chain rule on it every single time. We led to a formula. I just invented this formula for you. Did you guys see it? It's kind of cool, right? Invented the formula for you. We did a composition. We can do that. We took the derivative here. We took the derivative. Invented the time. We led to a formula. I just invented this formula for you. Did you guys see it? It's kind of cool, right? Invented the formula for you. We did a composition. We can do that. We took the derivative here. We took the derivative here. We know that to get dy dx. We did a composition. We can do that. We took the derivative here. We took the derivative here. We know that to get dy dx, we multiply those two things. then we just do our substitution back in for u. What that says is, if you want to take the derivative of some expression raised to some power, all you've got to do is take the derivative of the expression times the derivative of the inside. That's what you're doing. Bring down the exponent as usual, then multiply by the derivative of the inside. That's what this says in English. Look what it says. Bring down the exponent as usual. Bring down the exponent as usual. Then multiply by the derivative of the inside. That's what that says to do. Rich, you have to feel okay with that. So do you have to show me all this to do it? No, I just proved it for you. This is kind of a proof for you to be able to do that. You get it? So in English, if you want to hear this in English, bring down the exponent as usual, as you normally do for the power rule. That's why it's called the general power rule. So bring down the exponent like it's a power rule. Just multiply it by the derivative of the inside. You just can't forget about the derivative of the inside, because this thing matters for sure. If you don't have the 6x here, does it affect your problem? Yes. Oh, heck yeah. Yeah, by a long shot. Okay, so that does matter. Bring down exponent and multiply by derivative of the inside. Would you like a couple examples to kind of work through this? And then after that, I'll show you some more applications of the chain rule, stuff that we can do with some trigonometry, which I know you're going to love, right? Stuff you can do with that, and that you can't forget that you need to do with that. I'll show you how to work with the chain rule. And then after that, we'll talk about implicit differentiation if there's a little bit of time. Okay, so let's discuss this problem. If I want you to find dy dx, which is
dy dx equals 4 times x cubed minus 2x plus 38 to the power of 3. D dx of, or I guess I'll do times d dx x3 x to the third minus 2x plus 38 d dx x third minus 2x plus 38. Oh, that's horrible. Plus 38 equals 3x squared minus 2. Four times x to the third minus 2x plus 38 cubes times 3x squared minus 2. I'll put that in parentheses. 12 dy dx equals 12x squared minus 8 times x cubed minus 2x plus 38 cubed. Let's see if I'm right.
This is what I want you to find. Could I just do this? Could I just take the derivative of this and this and this and leave it to the fourth power? The answer is no, because this is a composition. Do you guys see the composition? This you could cover the whole thing up and call it u, or sorry, call it u to the fourth. Y would equal u to the fourth, and u would equal this stuff. Does that make sense to you? We could do the chain rule here. Does this fall into the category of general power rule? Is it some function raised to an exponent? That's what we're looking for. You guys see the power rule in it? How we get the power rule. That says, here's what we're going to do. We're going to do the power rule just like we normally would. We'll bring down the exponent, we'll subtract 1 from it. Just don't forget to multiply by the derivative of the inside. So you tell me what to do now that we've talked about it. What do I do?
Bring down 4.
Good, 4 goes down. Do I still have an expression here?
Yes.
What's going to be on the inside of my expression?
U minus 3x.
Do I change this at all from here to here? No, that's because that's the u, right? And you're going to be substituting back in for the u ultimately at the very end of any problem. So that inside, that's not going to change. That's this. Look at it. See how we still have a u and we substitute back in the original function to that? That's the original function here. You're still going to have that. So far, so good? Wait a minute. Right now, this is so far, so good?
No.
What's wrong? Don't really, you know what the biggest mistake people have? People do this, they bring down the exponent and they forget to subtract from it. Derivatives are not that hard, right? In doing the general power rule, you know you're supposed to bring it down and subtract. But people always forget the exponent. Don't forget the exponent. So we do bring it down, sure, but that 4, that was an exponent of 4. We subtract 1 from it, we're going to get 3. Is that okay? Are we done now?
No.
No.
We're good
Multiply it by
though. We
the
bring down the exponent, we subtract 1 from it, and now you get to do this part. The derivative of whatever the inside is. The f of x is the inside of your general power rule. It says, do this, do the power rule, no problem, leave that alone, and then multiply by the derivative of whatever was inside. Well, let's see. We got 4. Got the same thing. Notice how the calculus is done. Do you see what I mean by follow the ddx? Do you see what I mean by that? It's all about where the ddx is. That's what your calculus is. So here, this is staying the same. The only thing we got to worry about is that over there. What is it?
3x -2.
If I leave it just like this, am I going to mark points off from you?
Yes.
Absolutely. Why?
Parentheses.
I need to have the parentheses firstly. That says I'm multiplying the whole entire expression. Now, you got a couple choices. You can move this thing out front, and you can distribute that 4 into there if you'd like. Just make sure you have parentheses around it if you do it. Does that make sense? So you might see a problem end like this. You might see a problem end like this. Or you might see the problem end like this. Just make sure you have parentheses there, or otherwise, yeah, I'm going to mark you off because that's a different statement. Now, your question is, which one do you want, Mr. Leonard? And I go, as long as you need to hear, I'm happy with your calculus. Now, I want one of these two. I want one of those two out of you. What I can't have you do, don't keep going. Okay, there's no way you should ever foil this into the, actually it'd be foil oil, right? Outside, inside, but you should never do.
Ooh, that's not good. I forgot the parentheses here.
Yeah, because that's
I've
just the
lost
third power.
points.
You can't break the order operations. Exponents come before distribution or multiplication does, okay? So you can't break this rule. But this would be perfectly appropriate. How many people feel okay with this so far? Are you ready to see that we've been doing this literally the entire time with our power rule? See, the general means encompasses all, right? So check this out. If I give you x to the 6th, just a simple example, and I say, why don't you take the derivative of x to the 6th?
6x to the 5th. Okay, let's see where you guys with this.
You know inherently that that is 6x to the 5th, right? Okay, inherently. It wasn't inherent, I guess, because I taught it to you.
No, I inherently
you
knew
know
that
it,
the
and-
whole time, actually. I'm just that good.
Less. But if you applied the general power rule of this, check it out. If you said, oh, well, that's a function in terms of x, I'll write that a little better so you can really see it. If I said that's a
Wait a minute. The derivative of x is 1, and you're multiplying 1 by the expression. Okay, I see that.
Function in terms of x, could
That
you
makes a
do
lot
the
of
general
sense.
power rule to an
So you move the 6 out in front, 6x to the 5th times the derivative of x. Derivative of x, move the 1 out in front, exponent 1 minus 1, 0, x becomes 1, 6x to the 5th times 1, 6x to the 5th.
answer is, yeah, you could. Check it out. You would do the 6, x to the 5th. Remember, that would be in parentheses, right? Because that's your function. Times the derivative of whatever's inside. Only this time the inside is x. What's the derivative of x? 1. That's why we didn't have to show that, because the derivative of the inside is always the same thing. It's always just x. Do you get it? We've been doing the general power rule. We've been doing the chain rule the whole time. It's just, it was simpler because we didn't have that inside. So that would become 1, and you get 6 x to the 5th. Interesting. We've been doing it. That's why it's called the general power rule, and we had the power rule before. You ready to keep going?
Yeah.
Okay. Let's try a few more. We're going to start building on this idea, though. Give me 2 ways to do that problem.
You could FOIL it and then find the derivative, or you could use the product rule.
Distribution is one of them. Give me another way. You have 2 ways to do
Or
this
no,
problem.
did I say power rule? Product rule.
As soon as I do this, do you still want to distribute?
Yeah, probably not.
No, in fact, if they gave that to you before, that would be how you
So use
had to do
product
that,
rule.
right? Because there was no way to get rid of that 3 for you without foiling that all out and then distributing. Or foiling at least this out and then using product rule. In fact, maybe you had to do that on a couple of your examples, and it's like, darn exponents. But now let's look at this for what it is. This is a derivative. Can you see a product rule in it still?
Yeah.
Can you see a general power rule in it right now?
Yes.
Question is, which one comes first?
General power rule.
Well, half of you are right.
Which half is the question?
That's the question. Which one, working from the outside in, which one encompasses more of the problem?
Product rule?
You should be able to say this. You should be able to say this whole thing has to do with,
Product rule.
does the whole thing have to do with the general power rule? Which means, is that exponent
not.
of 3 applied to the whole thing right now? Then that does not come first. Is the product rule applied?
It's like the quotient rule thing before, because you have to do both. But like here, you don't have to worry about it. So it'd be like 2 times x squared minus 5 plus 2x minus 3, and then this is the problem. Say this is u. 3x, wait, 3x squared minus 5. Let me have the whole thing. Alright, nah. Squared times the derivative of x squared minus 5 3 x squared minus 5 squared times 2x 6x times x squared minus 5 squared. So 2x squared minus 5 plus 2x minus 3, 6x times x squared minus 5 squared. 2x squared minus 10 plus 2x minus 3, 6x times x squared minus 5, x squared minus 5. 2x squared minus 10 plus 2x minus 3, 6x x to the 4th minus 5x squared minus 5x squared minus 10x squared plus 25. 2x squared minus 10 plus 2x minus 3, 6x to the 5th minus 60x cubes plus, what's 25 times 6? 150? Oops. Yeah, 150 plus 150x this thing gets kind of crazy. 2x squared minus 10 plus, geez, okay, 12x to the 6 minus 120 x to the 4th plus 300x squared minus 18x to the 5th plus 180x cubes minus 450x. Bruh. 2x squared minus 10 plus 12x to the 6. I wonder if there's an easier way to do this. Minus 120 x to the 4th plus 300 x squared minus 18x to the 5th. Or let me reorder this. Actually, this entire thing. 12x to the 6 minus 18x to the 5th minus 120x to the 4th plus 180x to the cubes plus 300x squared plus, well, let's add these together, 302x squared minus 450x minus 10. Crazy. dy dx. I doubt I either did this wrong or he's not going to do this half.
If I do the whole thing right now, then that comes first. Does that make sense to you? It'd be the same as this question. Which one would come first, a general power rule or a quotient rule? What do you think?
Quotient rule.
Definitely yeah, the general power rule is only applied to this little top part, right? It doesn't encompass the whole problem. The quotient rule encompasses the whole problem. That would come first. Work from the outside inside. Now, if I did this, you'd hate me, first off. Which would come first in this
General
case?
power rule.
Chain rule.
Chain rule. In our specific case, this would be,
Chain rule,
you could
yeah.
say chain rule, that's fine. This would also be called the general power rule. Do you see it? General power rule, and then you would do the quotient rule.
Then general power rule.
And then general power rule inside of that. Yeah. Okay, that would be nasty. One way that you could make this easier if you're looking at it, you could take both this exponent, say, okay, this is now to the 10th, and that's to the 5th. That might make it actually a little bit easier. But starting out, you would see the general, I'm just making a point here, you'd see the general power rule first. Do you see what I'm talking about? You see the product rule first here. It encompasses the whole problem. And that's how you diagnose these things. What do you do first? Whatever's encompassing the whole problem. And then you work your way inside and you follow the DDX, and the DDX will tell you what to do. Are you ready to do this problem? Let's do it. So first thing we see, okay, connecting this thing is a multiplication. That means a product rule. Set up the product rule. Go for it.
So now
This one?
the cube root of that is going to stay in with that function.
Just do the product rule right now, and we'll talk about the next part later. Just do the product rule and set it up. Don't take the derivatives yet, just set up the product rule. Okay, set up the product rule. I want you to take don't do the derivative, just set up the product rule. The product rule should say the derivative of the first times the second plus the first times the derivative of the second. Were y'all able to do that? So this is what I mean by that. The derivative of the first times the second. Is that the second? No.
Okay.
That's the second. Yes. That 3 has to tag along with that piece if you're going to do the product rule. Raise your hand if you got that far so far. Okay, good deal. You have the exponent, right? Then you do a plus, and you do derivative of the first times second plus the first times the derivative of the second. Do you? Yes. For us, here's what it said. This was the first function in x, and this was the second function in x. It was being multiplied, right? So you have to take those two, just those two pieces. That's what you were doing here. Kind of crooked, aren't I? I'm always like that, I think. How many will feel all right with this so far? I'll try to be more straight on the next one. Now you follow the DDX and you just do what it tells you to do, because that's your calculus. So we just take derivatives piece by piece as they appear. So piece by piece as they appear says, can you take the derivative of this thing right there?
Yes.
That's actually quite an easy one. What's the derivative of that?
2.
So this says, all right, 2. Do I take the derivative of that? Heavens no. No, it has no DDX.
Did I forget the cubes? Yep, okay. Oh man, that's not fun.
Do I take the derivative of this? So I just write it. And now we get down to this piece, and notice how it's basically, the product rule lets you break it up as problems within problems within problems. None of it's going to get any harder than this. It's just you might have more rules encompassing it. So if you can follow the rules down, you know the 3 rules, the chain rule, quotient rule, product rule, you know how to go from the outside inside, just follow your DDX, you'll be okay. Now, that's easier said than done, or I know some of these problems are very tasking. But if you can do that, that's the fundamentals here. You look from the outside inside, start with the big rules, and follow the DDX, and then use rules within rules within rules. So on this one, we look at this and you say, can I do that piece, that derivative? It's basically a problem within a problem. What's the derivative of x squared minus 5 to the third? What rule do you need for that?
General power rule.
Chain rule, or the
General.
corollary to that, because it's a specific version of the chain rule, is called the what? General power rule. So this was a product rule, and inside of that had a general power rule. General power rule says, well, what I'm going to do is, so for this piece, what do I do? So notice I'm here right now. I bring down the 3, very good. What do I have next, please?
Squared minus 5.
Good, I don't change the inside. I don't change that to the what exponent? Oh, don't forget that. And then I'm done, right? Ah, okay. Times the derivative of the inside. That's the chain rule. That is the general power rule. Times the derivative, and I want you to write it out. I want to see this. I don't want you doing the math in your head right now. We're just barely learning it. Okay, I know that eventually some of you are going to be able to just do these in your head. In this class for right now, wait till you get to 4B to do that. For right now, I want to see your work. That way, if you make a mistake, I'm not saying you will, but if you do, I want to see where that's happening. Do you get me? Do you get me? Show me those steps. Okay, times the derivative of x squared minus 5. Remember that we're multiplying here. Are there any other ddx's to take care of? Hmm? Yeah, okay, I hope so. Yes, we do. We have a ddx. What's the derivative of this little piece? So if you follow that ddx down, that tells you where to take the derivative of, or what to take the derivative of. So we're basically all done up until that point. We have 2x squared minus 5 to the third. Let's not mess up any exponents. 2x minus 3 times 3 x squared minus 5 to the second times, what is the derivative of that little piece? Notice how we kind of eliminated. Some of the bigger rules, right? Right off the bat, we used product rule that helped us down to just have one more rule left. We had general power rule. Now we have just a very simple power rule, and we're good to go. Raise your hand if you feel okay with this so far. Your calculus is over with. Now we're going to make it prettier by using a little bit of algebra, and you're going to see something that happens often when you have a product rule that involves a general power rule. You're going to see some pieces that keep reappearing. See how that thing appeared again with our product rule? Because you had the original, and then you took a general power rule where that piece shows up again. A lot of times that happens when you do the product rule and you have a general power rule. You're going to want to factor that at the end. It makes things a lot nicer. So I'll show you what I'm talking about. If we go ahead, maybe make this just a little bit prettier, we have this. This becomes 6x. Like that.
It's a better way of writing it, for sure.
Are you okay with that so far? Yes, no? Do you see the factorization of what I'm talking about?
Yeah.
We have this big factor and this big factor right there. We can pull out, what can we pull out of that? If I pull out the x squared minus 5 squared, what I end with is 2.
True. 6x 2x minus 3 times x squared minus 5 squared. Pull out an x squared minus 5 plus x squared minus 5 2x squared minus 5 squared plus 6x 2x minus 3 x squared minus 5. Wait. I can pull out 2. Yeah.
Two still there. X squared minus 5 to what power? 1. Good, because I pulled out 2 of those things. Does that make sense to you? Plus 6x, 2x minus 3. Are there any of these left? No. I've factored that out. Notice you could get the same thing if you just...
Okay, that's how you write it. Okay. Yeah, that was kind of weird how I wrote that. So that's all you can do with it. It doesn't cancel out or anything because it's not an equation.
This distributes and give you this distributes and give you that. Okay, so that's factorization right there. Raise your hand if you feel all right with that so far. The next thing you do, distribute this and combine like terms. If you distribute this and combine like terms, you'll have a much simpler looking polynomial.
Oh, that's true, huh? Didn't think about that. Jeez, you can go really far with this. 2x squared minus 10 plus 12x squared minus 18x. Um, 14x squared minus 18x minus 10. And yeah.
So in here we get our 2x squared minus 10. We get our 12x squared minus 18x. If I did it right? Did I do it right? If we combine some of those like terms, I'm seeing 14x squared. I'm seeing minus 18x minus 10. Now, hopefully it's not just me, but this thing looks a whole lot more concise than that thing, does it not? It looks prettier, it looks better, it looks more concise, more wrapped up. And that's where we want to end our derivatives if we can make it that far. Show of hands, how many people feel okay with what we've done so far? At least up to the calculus being done part. Are you okay with the calculus being done part? After that, it's just algebra, some manipulation. That's okay. We can do that. By the way, this is the part where people lose track in this class what you're actually doing. Okay? They just get to they go, oh yeah, general Robb rule and Park rule and Quotient rule and chain rule. They lose track of what you're doing. What did we just do? We found the what? The slope. That's all we're doing. Find the slope. This is the slope. This is the formula for the slope of that curve at any point that I want. So could I still find the equation of a tangent line at a point? Sure. I plug in the x coordinate to here to find my slope. I plug my x coordinate into here to find my point. Value. Then use y minus y1 equals mx minus x1. That's all we're doing. Okay, we're finding slope. Or if this is a position curve, we're finding velocity or rate of change. Or if it's a cost function, we're finding marginal cost. Yeah. Marginal profit, things like that. Very interesting stuff. Let's try a few more. I need to show you how the
wait, what kind of graph is that called?
Finding
where you find
marginal cost. Slope. Sure, if it's a cost function, we're finding
cost function.
Marginal cost, marginal profit, things like that. Very interesting stuff. Let's try a few more. I need to show you how the chain rule is going to affect something to do with like a trig function, and that will probably be about our day.
Oh wait, I didn't hear what he said. Something about a trig function. I don't know if I like that. That doesn't sound too fun.
Does the chain rule still apply?
Yeah, probably if you just turn that square root into a half exponent. I don't see why not. Five x squared minus 1 to the power of half. Y equals half 5x squared minus 1 negative half times the derivative of 5x squared minus 1 half 5x squared minus 1 negative to the negative half times 10x five x times 5x squared minus 1 to the power of negative half dy dx
What do you think? Do I have a function within a function, basically? That's what you're asking. Because if you do, then you have a chain rule. Do I have a general power rule here? Oh, explain that. Explain how I have a general power rule, because I don't see an exponent right now. So in order to do this, well, hopefully you remember this from the last couple sections. In order to do the derivative, you really need to represent roots as exponents, right? Because we know we deal with that. We subtract 1 from them. You can't subtract 1 from a square root unless you write it as a 1/2. So first thing to do is go, yeah, all right, I know that this is 5x squared minus 1 in parentheses to the 1/2 power. And that right there says, aha, aha, look, if you can cover it up, you're talking about a composition. Within parentheses, you're talking about a composition. That means chain rule applies. In this case, it's an exponent, so the general power rule applies. Why don't you go ahead and try it? Go for it. You're at that point at this stage. Remember, I really don't want you doing the work all in your head. I want to see the steps right now. I want to see the ddx written out. Did you make it that far? 1/2 5x squared minus 1 to the negative 1/2? Cool, inside doesn't change for now. And then we take the derivative of the function itself, the inside function of our composition, or the piece of our composition. If we take that derivative, then we're just about done. Did you get the 10x too? How many people got exactly that on their paper? Good for you. Now make it a little prettier. Here's how you can make it a little prettier. The 1/2 and the 10, that simplifies. That simplifies and gives you 5. So we have 5x, and then we have this 5x squared minus 1 to the negative 1/2. How you can write that appropriately would be, since you started as a square root, you probably want to end with some sort of root. We want 5x on the numerator, 5x on the numerator, 5x squared minus 1, and a square root on the denominator. You see why it's on the denominator firstly? Is it negative 1/2 that moves to the denominator? The 1/2 becomes positive, that's a square root. Can I cross out the 5x and the 5x squared? Oh, heck no. No. We can't do that. All right, I see that all day long. All right, angry. But no, we can't do that. Are you ready to move on? The general power rule, because that's about all I can show you with that. I mean, it doesn't change after this. If you can do these couple problems, You're okay so far. Are you okay so far?
Would leaving it in exponential form still be acceptable?
If it's given to you that way. What I'm expecting most of the time is if I give it to you as exponents, exponents are fine. If I give it to you as roots, change it back to root.
Right. There.
derivatives. Can you do that derivative? That would be what, folks? Oh, very good. You're memorizing it. Fantastic.
Wait, what of it? Mega sine x, yeah.
Can you do that derivative?
Can you use general power rule for this? I don't want
The
to draw
answer is
anything.
no, not with what you know.
Oh, okay.
Well, actually, yes, because we just talked about chain rule, but not what you knew before today. The answer
Oh.
would be no. But let's look at it. Do you have a composition going on in this? Which means, can you cover up a piece of it and get some other function, basically? If I cover this part
okay.
up, if I say cover up the inside, we always talk about covering up the inside. Cover up the inside, and I say, well, let's let
U.
y equals cosine of u, and u equals whatever's under my hand. Would that be an appropriate composition? Because if I let the u go in for u, in fact, x to the fourth go in for u, then I get that back again, right? Well, if we find our dy du, what's dy du here, ladies and gentlemen? We just talked about it. Negative sign what? U. Negative sign u. And du dx. What's du dx? And we knew
dy du equals negative sine u. U equals x to the fourth. Du dx equals 4x cubed.
that dy dx is dy du times du dx. True? True story. This du dx is dy du times du dx. True? True story. This is negative sine u, because that's dy du, that's this, times du dx, which is 4x cubed. dy du, du dx, dy du times du dx. That's chain rule. We just talked about that. That's this right here. What's the one last thing that I need to do? Why do I need to substitute? Don't want to end with u's and x's. We'll make it prettier, but that's the one I want to talk about. This will ultimately become negative 4x cubed sine of x to the fourth. That would be the derivative of that curve. Are you okay with how to do that? Do that 4x cubed out front. Notice what you can't do. Oh, please, goodness, don't do this. Please don't, please don't ever multiply those. That's an angle. This is not. This you cannot make 4x to the 7th. If you do that, I'm going to burn your paper. I'll burn it. Gone.
And then kick
What
it.
the homework? I didn't see any homework from you. I was just burn it. It's an embarrassment. I want you to do that. Just kidding. I wouldn't burn it. But I will go, no, with like 5 exclamation points and underline it and scribble on it and stomp on it. That's about it.
And then kick a puppy.
I'm not going to kick a puppy. not that bad, but. Are you okay with this? Here's what this says in English. We'll stop here. This says, in order to do the chain rule with this type of thing, you really don't need to show me this. This is just the underlying work. Here's what it says in English. Well, and a little bit of calculus. It says if you want to take the derivative of a composition such as we just had right now. Here's what this said to do. It says, I want you to take the derivative, look what it does, please. It says, take the derivative of cosine, right? What's the derivative of cosine? Negative sine, and leave the inside alone. Does that look familiar? That's exactly what we do with general power rule right there. Take the derivative of the outside function, the cosine in this case. But then you just can't forget to multiply by the derivative
Inside
of whatever
derivative.
the inside was. And that's what this says. Take the derivative inside and multiply it. That's what we did with general power rule. A lot of people do this. They will give me they give me this all day long. Oh, it kills me. They say, oh yeah, answer is negative sine of 4x cubed. I get that all day long. See the common mistake that people would make to get that.
How?
They go, oh yeah, derivative of cosine, negative sine. Derivative inside, 4x cubed. Is this right? No, because they have not applied the chain rule. Chain rule says you have a composition here. You need to take the derivative of your function, sure, leave the inside alone, then multiply by the derivative inside. So this says you take, I'm going to use a kind of combination of rules here, or notation. You take f prime of x, f prime of g of x, times g prime of x. That's what you do. Derivative of the outside, leave the inside alone, times the derivative of the inside. And that's exactly, do you see that over here? Do you see what that means for us here? Okay, good. Derivative of the function times the derivative of the inside, and that's what we're doing. How many people feel okay with what we talked about so far? I will start here next time with a couple more chain rules, and then we'll keep on moving. Right? So today, we are practicing. All we're practicing today is applications of the 3 rules that we talked about. Chain rule, which includes the general power rule, the product rule, and the quotient rule. That's pretty much it. What you know from the chain rule is this. This says in English, you take the derivative of the function, leaving the inside alone, and you multiply by the derivative of the inside. If you can remember that for the chain rule, you're good to go. We'll start simply, then I'm going to start building on some nasty looking problems. Oh my gosh. And they'll take us maybe the whole board to do. But you need to see them because your homework should be like that too. Okay, I don't want to leave you hanging on this stuff. So we're going to do examples. We're going to do examples pretty much all day.
Yay! Homework. So excited.
Okay, sine of 4x to the 5th. A couple questions for you. First thing, is this a product rule?
Oh, definitely not. No. I could see how people do that. Um, first thing, the outside function. Find the derivative of that. It is cos x. Leave the inside alone though. Times the derivative of the inside 4x to the fifth. Cos 4x to the fifth times 20x to the fourth. 20x to the fourth times cos 4x to the fifth.
Okay, so approximate doesn't apply because this is actually a function. This is really a composition. You know, a lot of people that really don't understand trigonometry, they go, oh yeah, it's sine times 4x to the fifth, which is not really what we're doing, right? You can't take,
Angle.
if I just give you sine, that's meaningless. That doesn't mean sine, that means a sin, right? Now, if I give you sine with an angle, that means sine, okay? I'm not gonna write sin on your paper. You're not gonna write sin. If you write sin without this, you're sinning. In math, that you're sinning, right? You have to have this part. You have to have something with it. If you just have this, that, right? That's not, sine by itself is meaningless. It must have something attached to it. So this is not a product rule. What this is a composition of two functions, a composition of 4x to the fifth into sine. What that means whenever you see a composition is a chain rule will work. If you can cover up a piece of it and you still have a function, that means it's a chain rule. You okay with that? That's chain rule right there. So if we use the chain rule says this. It says in order to find dy dx, you're going to take the derivative of the function, yes, but you're going to at first leave the inside of it alone. So what's the derivative, everybody, of sine?
Cosine.
So we do the cosine, yes. Do we take the derivative of 4x to the fifth right here?
No.
That's going to stay alone. That's this part. Okay, that's the g of x. That says 4x to the fifth. This says you don't even change g of x, and we didn't change g of x. Times, the derivative of g of x. That's where you get the derivative of the inside. You don't mash it all together. You don't take this derivative and the derivative and put it right here. That's not what you do. This should be cosine of 20x to the fourth. That's not it. You take this derivative later, and you multiply it. And I want to see it written out, 4x to the fifth, like that. And then you take the derivative. What's the derivative of 4x to the fifth? That's where we're getting that from. So we're going to have a 20x to the fourth times cosine, don't even need that times, of 4x to the fifth. That right there, that's our derivative. That was a chain rule.
So on the test, you would see ddx.
Yeah, you absolutely want to see that.
Okay.
The way I'm showing you things in class is the way I want to see them on your test. Because I'm going to grade each little part. I'm going to look for this. I'm going to look for this. Right? There's only 2 steps. Don't get lazy and not show me your steps. You okay with that one? Okay, that's a pretty basic one. We're going to start building them up now. I'm going to start incorporating more and more rules so you can start seeing them. You ready for it? Yeah. Let's do this. You know, a really good note to write down here, or at least think about? You want to think about the rules that you're going to have to do before you start your problem. Mostly you think about the most encompassing rule here. So when you look at this problem,
Okay. Oh, I'm out of space. Crap. New. Okay, so first I'm saying the chain rule, because we have the cos function and the x to the fourth function. That cos squared. So there's two. Okay, there's two of these. Yeah. So actually, product rule might be better. You can rewrite this as cos x to the fourth times cos x to the fourth. Yeah. d dx. Write really small. Cos x to the fourth times cos x to the fourth plus cos x to the fourth times the derivative of cos x to the fourth. Okay. And then off to the side, we can do the derivative of cos x to the fourth. This would be the chain rule. So I want to do the derivative of cos negative sine, leave this alone, times the derivative of x to the fourth. Negative sine x to the fourth times 4x cubed. Negative 4x cubed sine x to the fourth. And that's only for this one at the top here. So d dx cos x to the fourth equals this. So I can substitute this. Negative 4x cubed times sine x to the fourth times cos x to the fourth plus cos x to the fourth times negative 4x cubed sine x to the fourth. negative 4x cubed sine x to the fourth cos x to the fourth plus cos, well, negative 4x, I could do this minus 4x cubed sine x to the fourth cos x to the fourth negative 8 x cubed sine x to the fourth cos x to the fourth dy dx. Slope of a curve at a point. Alright, let's check it.
What does this actually mean? What is the cosine squared x to the fourth mean? Write it like that. Give yourself a chance of this problem. Instead of just leaving it like this, maybe you write it as cosine x to the fourth squared. Because that's what it really actually means there, doesn't it? We just take a shortcut and put that square there oftentimes. You okay with that so far? Now let's think. Start with our rules. Which rule encompasses the whole problem? Is it a chain rule? Is it a general power rule? I see two of them right now.
Rule.
But I'm going to use a specific, I know they're both chain rules, all right? So we're going to be more specific than that. Which one should we do first? This part, or should we do the 2 first? The 2. And what does that 2 say to do? That's the general power rule. Now, it is a chain rule, but it's a specific chain rule. It's like a corollary to the chain rule. It's called the general power rule. So what this says is, if you can cover it up, remember that? It's a chain rule. It's a specific chain rule because it has a power.
I guess you could. I wonder if I was wrong then. Let's see. D dx cos x to the fourth squared two cos x to the fourth, and then find the derivative of that. Cos x to the fourth. I think, is that what I found? Yeah, I already found this. Yeah, okay, it'd be the exact same thing. It's just mine took a lot more work. This is negative 4x cubed okay, then this uses the chain rule. Okay, but I already did this work. Negative 4x cubed sine x to the fourth. And then if you put that on top, multiply them. Negative 8x cubed. What did I put first? Sine x to the fourth. Cos x to the fourth. Dy dx.
It's this general power rule.
Then change it.
General power. And then inside of that, you're probably going to have a chain rule. Do you see the chain rule as well? If we start with the largest rule, I'll say largest because it's the one that comes with everything. You start with that, then you can follow your ddx. But it's all about how you start. You got to think about that first. You with me? So let's go ahead and do our ddx. What happens to this thing? What are we going to do?
Move there.
So this 2
Drop down.
goes out front, all right. And I'm gonna have, what's next? Come on, tell me. Does this change for my general power rule? So I'm still gonna have a cosine x to the 4th, to what power?
So no, power.
So do I need a bracket with a little 1? Is this okay on how to get there? And then I'm done? No what?
Times, the derivative x to the 4th.
Of just x to the 4th?
Cos x to the 4th.
What's the derivative that should come next? Remember when you do a general power rule,
Cosine.
you cover that whole thing up, right? You go, okay, take the derivative of what's under my hand. It says you move the 2 down, you subtract 1 from it. That's great, and you don't change what's under my hand. That's this part. But then you have to take the derivative of everything that's under my hand. Do you get me? So it's not just x to the 4th, it's what?
Cosine.
The whole thing.
Oh, this is gonna be brutal.
No, not brutal. Fun.
Tonight.
Yes, tonight. Raise your hand if you're okay with that so far. You see why you have a cosine.
Then you're gonna use the chain
Do
rule.
you see why you have a cosine there? This one you do not change. This one
Find
you take
the
the derivative of the
cos
entire
x,
inside function. That's how the general
multiply
power
that by the
rule, aka
derivative
chain rule
of
works.
the inside
Derivative
x
of the
to the 4th.
function times the derivative of the inside. But now you're done with the calculus up to this point. Now you follow your ddx, and this has broken down your problem, made it a little bit easier. Can you take the derivative of cosine x to the 4th?
Yes.
What rule is that?
Chain rule.
That's the chain rule. The chain rule says you take the derivative of your function times the derivative of your inside. That's what it says to do. The derivative of your function times the derivative inside. So you tell me, does any of this change? Times. We'll take the derivative of cosine x to the 4th. What's the derivative of cosine x to the 4th? Let's think about that. It says you take the derivative of...
Sin x to the 4th
It says the derivative of your overlying function. Okay,
4x
that's the thing that you're composing into. So derivative of cosine, you need to take that first. What's the derivative of cosine?
Negative sine.
Okay, so I'm going to put that in a bracket because it's negative. Negative sine. Hey, negative sine of what? Is it still x to the 4th or 4x cubed?
X to the 4th.
Good, because chain rule says you do this, but you leave this piece alone for just a second. You leave that alone. In order to find the derivative of this, you multiply by that. So we're starting to build these rules on top of each other, and you really got to be good at what rule comes first. If you are, then you follow the DDX, and it's just fine. But you got to find that first rule. Once you do that, we said, okay, this probably should be written like this. This says general power rule. You bring it down, you leave it alone, you multiply by the derivative of the inside. That's where we're getting that from. You okay with that? After that, calculus is done. Just keep on writing. Keep on writing. This DDX says take the derivative of this thing. Now this is a chain rule. Chain rule says I take the derivative of cosine. Got it? But I leave the inside alone. Just like you left the inside alone here. I leave the inside alone. And then I multiply by the derivative of the inside. That's where that's coming from. Rich, I feel all right with that so far? Good, all right. We're almost done. We only have one little teeny derivative to take. What is it?
X to the 4th.
Yeah, you know what? Every time you do a step, it makes it easier. Sometimes. But every time you use a rule, it breaks it down in little pieces for you. Times, what is that?
4x.
Cool. 2 cosine x to the 4th times negative sine x to the 4th times 4x cubed. Just make it maybe a little prettier up here. A little prettier would mean you have a negative, you've got a 4x cubed, and you have a 2. They're all being multiplied together. You see the multiplication? Take that stuff together. So this will be 8 negative 8 x to the 3rd then the cosine, or the sine, and then the sine. And that's how I'd like to see your problem. After this, it's just algebra. It's just putting a couple things together. You have 2 times -1 times 4, that's your coefficient, that's -8. The x to the third, we typically like to bring that up front. Can you follow that? Yes, no? If yes, great. If not, do you have a question about it? You guys are here? Are we good? My middle guys? You good? People at home? Just kidding. Can't see you. You guys on the left? What if I could see you? That'd freak you out, wouldn't it? People in the world. Anyway.
Doesn't matter which order the sine and the cosine go in.
No, that doesn't matter. No, this is technically right. This is it. So no matter how you, because multiplication is commutative, associative, doesn't matter how you group them, how you put in order, we typically just write numbers and single variables first, and then sines and cosines. That's just how we do it. Can we move on? Are you ready to move on?
To one similar.
Guess you could just leave. You're gonna stay, no, no choice.
Okay. ddx of tan 3x squared minus 2x. Okay, this just seems like a chain rule. I'm not seeing any other rule yet. Only thing is I forget what the derivative of a tan x is. Let me look that up. Secant squared x. Is it really? Secant squared of x. Okay. So we got secant squared of, leave that alone. Chain rule. Multiply by the derivative of the inside, which I'll do in a second, times the derivative of 3x squared minus 2x. Secant squared of 3x squared minus 2x times, this is 6x minus 2. What are we going to do with this? I wonder if he's going to make a point like you can't distribute these because it's an angle or something. It does that a lot. Probably move this out to the front. 6x minus 2 secant squared of 3x squared minus 2x. That doesn't look too good. Doesn't look the best. There's probably a better way of writing this, but we'll see what he does.
Okay, okay. This is actually kind of a more friendly problem. A little bit. Do you see why it's a more friendly of a problem?
Only one rule, chain rule.
If I had done this, would it be a friendly problem? No, that would be your enemy. If I did that, what would you do first? A chain rule? They're both chain rules, but
General
a chain
power
rule
rule.
or a general power rule? That would be just very similar to that problem. You would have to bring down the 4, all of this to the third power derivative of the entire inside thing. Do you see it? Without the power, what are we talking about here? That's the chain rule. Do you see if you can cover something up and you still have a function, that's typically a chain rule. So we still have a chain rule right here. It's not a product rule. That's not a product. It's tangent of something. That's a chain rule. It's composition. Well, let's do it. How's the chain rule work? What should we do first, please?
Take the derivative of the outside function.
Okay, cool. So leave this alone. Take the derivative of that thing. So this says I'm going to have, tan. What's tan?
Secant squared
Very good.
x.
Make some flashcards. Know those derivatives. Secant
I do not know
squared.
those derivatives.
Does the inside change for us right now?
No. I'm sure I'll know them when I actually take calculus.
No.
Surely.
The inside of the inside.
Can you tell me what the inside is here? Is it tan of this or just this? Just that part. This is just a chain rule. It says derivative of tan is secant squared, leave the inside alone, then multiply by the derivative of the inside. That's what the chain rule says to do in English.
Parentheses. Okay, good.
Got it.
Brackets.
Secant squared, cool. Inside doesn't change, derivative of the inside. That's the chain rule at work. Not too bad. What are we going to do? Just follow the DDX. This is basically done. You're going to get a secant squared. But what people often forget to do is this piece of it. They really often forget to do the chain rule.
Really?
They'll do this for me,
Huh.
but they'll forget this part. I can't have you forget that part. That's a big part. That's a really big part. Or they will do secant squared, and then they'll take the derivative and just mash it together. So if you're giving me this,
Yeah,
well,
that's dumb.
that's not even nearly right. You changed the angle. You've messed that problem up. All right. That's not what we're talking about. You can't just take derivative of this
That's
and
not the
derivative of
chain
that.
rule.
This is definitely a chain rule because it is a composition. You see the difference there? Okay. So for us, we go no, not that. This is what is it? Oh yeah, I just wrote it. Another question: can I distribute that?
Yeah. Yeah. You have to be careful.
No.
Why can't you?
It's a angle.
What is that?
It's an angle.
It's
Angle.
an angle. It's actually an angle. That's
Oh wait, did he
related.
actually?
What?
Why can't you?
Why can't you? Another question: can I distribute that?
I knew it.
Yeah.
I know Professor Lunderman. Pre-watch.
No. Why can't you?
Why can't you?
It's an angle.
What is that?
It's an angle.
That's an angle. It's actually an angle that's related to
Oh,
this.
no, not this.
I mean this.
I thought you meant
No,
distribute like
these
the
two.
whole thing. Okay.
Can you distribute these two?
No.
Negatory. No. This, that's not an angle. This is attached to that secant squared, okay? That's part of it. You can't change the angle. You can't change the angle. What we can do is move this to the front so that we don't distribute it. You probably wouldn't want to take this thing in and you take the whole thing. You wouldn't want to do that. Okay, it's already factored for you nicely. Don't do that. Just leave it as 6x minus 2 secant squared 3x squared minus 2x. Tell me one huge thing I'm going to mark you off on.
Parentheses.
Yeah, for sure. Still okay? All right. Ready to keep going?
Couldn't you also put the secant in parentheses?
That?
One parenthesis, right? Yeah, like that.
Like that?
Yeah.
You could? It would be irrelevant, but you could.
And just keep it easier.
Did I do that? I did.
Okay.
I like that. Parentheses.
See, now I'm having fun. Sort of. Oh, really? No. You know what? I'm not gonna be nice. There.
Great way to
What?
say it.
Aw, man. Alright. My brain's running out of focus. Let's see if I can get through half an hour more of this. cubes plus cosecant x power 3 on the derivative of this thing. So first thing to do is probably turn the square root into an exponent. And use the general power rule. Sounds like a great idea. So move that to the front. Half x cubed plus cosecant x cubed minus a half, and then multiply that by the derivative of x cubed plus cosecant x cubed. Oh, dude, come on, man. It's annoying. Okay. So this is not a derivative anymore. Luckily. So this is fine for now. Well, no, we can't distribute this because it has an exponent on it. Okay. Cosecant x cubed. This was originally a square root though, so we probably want to put this on the bottom. It'd be like half over square root of x cubed plus cosecant x cubed. So this part's fine. Now we're worried about the right side, finding the derivative of this. We can split this up by addition. So we can find the derivative of x cubed plus the derivative of cosecant x cubed, which is going to use the chain rule. X cubed plus cosecant x cubed times, this one's easy, derivative of x cubed 3x squared plus plus yeah, it's gonna be a chain rule. So cosecant, derivative of cosecant, the outside is a negative sign, leave the inside alone. Multiply by the derivative, one more derivative, that's it, of the inside, which we already found before, but I'm going to do it again because why not? Because I'm acting like I'm in his class, and this is the work you gotta show, I guess. Write this thing again. X cubed plus cosecant x cubed times 3x squared plus this is a lot already. Negative sign x cubed times 3x squared Write the same thing over here. x cubed plus cosecant x cubed. I'm going so slow. I'm like out of brain juiced. Straight up. Negative 3x squared sine x cubed. Okay, we're getting somewhere. No more derivatives. Just algebra. Half square root of x cubed plus cosecant x cubed multiplied by, jeez, okay, I'm gonna, too many steps. This can go away, this can go away. I'll, yeah, like that. These can't be combined. Factor out of 3x squared? Is that the play here? Do we go 3x squared negative sine x cubed? Is that like, is there a point to that? Or I guess it would be 1 minus sine x cubed. You know, I guess you could, but there's not a point. So I'm not gonna do that. So actually, what will be the best form for this? Probably half times 3x squared minus 3x squared sine x cubes all over square root of x cubed plus cosecant x cubed. Distribute the half. 3 over 2x squared minus 3 over 2x squared sine x cubed x cubed plus cosecant x cubed. Is that the best form? That's the best I can think of. You could factor out a 3x squared if you wanted, but like, what's the point really? I think that would look dumb. So dy dx equals okay, let's see.
I was just going to give you an X, but I want you to see what happens. So this will be a little bit more difficult. Trust me, you want the more difficult ones now. That way your homework seems easier. If I just give you all the easy ones now, your homework should seem like a bear. So you want to do that. Okay, I'm lost. What do I do?
General power.
Why would you say general power rule? Okay. So chain rule, general power rule, same thing, but we're going to say general power rule when we have the exponent so we can classify this a little bit better in our heads, okay? So if I say chain rule right now, I'm looking here, I'm looking there. So this, I'm going to call that a general power rule for this class. Okay, okay? Do you see the general power rule at work? See how it covers the whole entire expression? So perhaps write it this way. Because we know in order to take these derivatives, we've got to have exponents. So far, so good? Am I? Oh, I am. Shoot. Better? Much more better. Okay, tell me what to do. Come on, you guys should be rolling with this stuff at this point. This should be like, okay, we're getting there. Not perfect, but we're getting there. What do we do?
Half in the front.
Good. 'Cause
Take the
this
derivative
is general
of
power rule,
the
right? General power rule says
side
bring it
term,
down.
multiply it by the entire expression.
Write whatever's on the inside. Notice how we're not changing that. The inside does not change for our chain rule, which also includes a general power rule. Do I still have an exponent?
Yes.
Or do I just get rid of that exponent? Do I still have an exponent here?
Yes.
Don't forget about that exponent, man. Oh my gosh. If you just move down to 1/2 and forget that, that's a big deal because you've eliminated the square root on the denominator there. So this really needs that negative 1/2. Do you see where the negative 1/2 is coming from?
Yes.
Can nudge your head.
Minus
You
a
feel
half.
okay with it? Now what do I do?
Or a half minus 1.
Okay, times derivative. Take that derivative. Yeah, take the derivative of the inside. Take the derivative inside. So general power rule says bring it down, subtract 1, just like you normally would with any power rule, only now you have to multiply by the derivative of whatever you covered up, whatever you ignored for a second. In this case, it's the entire expression. So notice how before you start taking all these derivatives, you have the same thing twice. Do you see that? Same thing twice, and then I'm losing some of you. You with me? Then you take the derivative of that little piece. This calculus done. Just hang on to it for a while. Now let's look at the derivative of
General-
this nasty junk here.
Or
What
no, no,
is
no.
the derivative of this
You
thing?
can
Can you
split
take
by
a
addition.
derivative piece by piece? Is it okay when I'm adding, subtracting?
Yes.
Do I need a special rule to take the derivative of x
No.
cubed? Not at all. I can just do what's the derivative of x cubed? Beautiful. So don't outthink these problems. The only time you need special rules is when you have a quotient, a product, or a chain rule. That's it. So when you get this little piece, this should be a problem within a problem. Now you look at this, you go, how do I take the derivative of x cubed? No problem. It's being added. Remember, derivatives are separable by addition, subtraction. That's okay. So I just take this and go, oh, yeah. I do 3x squared. Not a problem. That's fine. Can I take the derivative of cosecant x cubed? Can I take it directly, or do I need a special rule for it?
Chain rule.
Do you see the chain rule here? Chain rule says, sure, it is cosecant, but if there's something special in there besides an x, that means a chain rule, because that's a composition just like this one was, just like, what's the other one? Just like that one was, just like this one was. That's a composition. You need a chain rule there. If you just give me the derivative of cosecant with x cubed, or the derivative of cosecant with 3x squared, you're not hitting the money on this class, all right? You're missing the chain rule. You're missing some factors of x. You're missing a whole lot of stuff here. So this is great, sure. Now let's take the derivative of cosecant x cubed. What's the derivative? The chain rule says take the derivative of cosecant. So what's the derivative of cosecant?
Negative sign. Oh wait. Is it actually? Oh, it's
Let me
cosecant.
change it.
Crap. Okay, that messes things up. How much? This is okay. This is when it starts getting messed up. Negative cosecant cotangent. That's annoying. Cosecant cotangent. Good thing it's still negative. Okay, maybe it doesn't mess it up that bad. Okay.
Into a bracket too. Negative cosecant cotangent of what?
X to the third.
Good, because this says with chain rule,
Did I keep that?
you take this
Yep.
derivative, great, I just do that, but you leave the inside alone for now.
Wouldn't that be cosecant
X to the third, cotangent X to the third.
Or is it okay to leave it?
Oh yeah, sorry. Did I forget? Oh, I did forget that. Shoot. I knew something looked funny. Thank you.
What?
So this says when you do this,
No.
cosecant is cosecant cotangent. So cosecant x was cosecant x cotangent x. What our x is x to the third in this case. So we go, okay, x to the third.
That's
the
fun.
third.
That's so much fun. Leonard, why? It's gonna look so bad, okay. Negative cosecant x squared. Cubed, not squared. Man. X cubed. This needs moved. And this needs moved. Okay.
Now what?
Thank you.
Multiplied by the derivative.
What's the inside?
X to the third cubed.
Sure, it looks ridiculous. Yeah, I know that. But can you do it? Do you see where it's all coming from? How it's all fitting together? Is it really, really all that bad? Not really. It's just you got to be careful, really careful. I mean, probably the hardest thing is memorizing cosecant. There you go. Hardest thing here
True.
is derivative of cosecant is negative cosecant cotangent. Hopefully that's right. Is that right? Just check your notes. Okay, all right. Because here, well, general power rule, sure, we got that down. Calculus is done. Here, derivative of this one's very easy, 3x squared. Derivative of this one, that's chain rule. This is negative cosecant cotangent. You do not change the inside. You multiply by the derivative of the inside. That's going to be 3x squared. That's where we're getting 3x squared. Are you with me on this so far? Okay, let's see if I have room for this stuff. I'm going to go right here. So 1/2 all this to the negative 1/2 3x squared negative cosecant cotangent and lastly we have that little piece 3x squared. Hope that fit. I think so. Sure.
Now the 3x squared, is that going to get multiplied with both of those terms? The x cubed plus...
You mean here and here?
Right. Or does it just stay with cosecant?
No, I'd say it's
This
just
right
one
here
term.
ends of parentheses right there.
Cosecant cotangent, it's
So
one whole term.
that 3x squared,
In fact, that
this
3x
3x
squared is part of the
squared
term.
is not associated with that x cubed. Right? So this does not get distributed to here. This right here is 3x squared plus this entire nasty looking expression. Okay, that's what that is. So when we try to simplify this just a little bit, let's look what happens.
Wait, hold on, what's these?
There's 3x cubed. Right, so squared. This 3x squared is not associated with that x cubed. Right, so this does not get distributed to here. This right here is 3x squared plus this entire nasty looking
I
expression.
think the guy was asking if you would do like negative 3x squared cosecant x cubed times 3x squared cotangent x cubed. It's just the negative cosecant cotangent thing is one term. And you could just move the 3x squared to the front, but you're not gonna.
Okay, that's what that is. So
You
when we
misunderstood.
try to simplify this just a little bit, let's look what happens. We're going to get 1/2 x cubed plus cosecant x cubed to the negative 1/2. We're going to get a big bracket. 3x squared doesn't change, you don't distribute to that. That was just a standalone small derivative 3x squared. This, we're going to pretty this up a little bit. Positive, negative, plus, minus, what's that going to be?
Negative.
Minus. I'm going to move the 3x squared out front. So this will be minus 3x squared cosecant x cubed cotangent x cubed. And that's your derivative. That's pretty nasty. Can you follow it? Yes or no? Yeah? Or like, whoo.
There's no simpler way to.
Would it be correct if you would go 3x squared minus 3x squared cosecant x cubed cotangent x cubed over 2
Sure.
times?
Now I'm going to show you that right now. So if you do want to put this back into this format, this would be,
I mean, like, do you want us to, or can we just leave it as that?
Because I mean,
at this point, it could go either way. If I give it to you as a root, probably make it back as a root. That's generally the idea. Give it to you as exponents, leave them to exponents. Also, one more thing, if some of you guys want to get fancy with this and factor out 3x squared, you'd have 3x squared times parentheses 1 minus
Yeah.
that.
That's what I was wondering.
Sometimes identities will help with that. Sometimes you can do identities. A lot of 1 minus stuff when you have squares happens. This thing, I don't know if you can simplify
don't.
that anymore or not.
I'm not sure.
Because I made stuff off the top of my head. But what you could do, one last final thing would be this.
Did I put the half on the? Okay, so for these fractions here, I definitely want to put the 2 on the bottom. Like 2 times, yeah. Looks way better.
If you made it there, if you can make it there, that's fine for me. That's great. So we did general power rule, we got it. Here's inside not changing, derivative inside, got it. We're going to do 3x squared, derivative, this is a chain rule. Chain rule says negative cosecant x, cotangent x, so we leave that inside alone, multiply by the derivative of the inside, and then after that it's a little bit of simplification. Originally I feel okay with this problem. Sure, they're nasty, yeah, I get it. I mean, they don't look fun, but they're useful. What did you just find?
So good one.
Yeah, slope. All this means is M. That's slope. M for this.
I think the correct way to look at it. I hate to be dealing with that graph.
Oh yeah, I don't even know what that looks like. Not a clue. A little bit.
Probably all the squiggly lines all over the place.
Don't know. Don't really care, honestly. You ready to keep going? 2 more. 2 more. What you want to do first? You want to do the hard one or the harder one?
Harder.
You want to do the harder one?
Definitely.
All right, you asked for it. We have 3 more actually.
What? Oh, brother.
The last 2 and the 1.
Yeah.
Three x. Wait, no. 3 plus. What?
Nope.
X squared. Cotangent x squared -3. Okay, so first thing, definitely general power rule, for sure. So -3. 3 plus x squared cotangent x squared, leave that alone. I'm gonna make these parentheses and then take the derivative of the entire inside here. So shrink this. D dx 3 plus x squared cotangent x squared. Oh, I forgot to subtract 1. That's not good. Good thing I caught that. Okay. So leave this. Well, just go as a fraction. -3 times 3 plus x squared cotangent x squared. Yeah, okay. Oh, this whole thing. Power of 4. Alright, good so far. Chain, no, split up by addition. D dx. And you know what, I don't feel like writing that out. So I'm just gonna say, this is the derivative of a constant. So 0 plus whatever. So basically just the derivative of x squared cotangent x squared. That's a product rule. Yeah. Fun. Okay, so this, I gotta remember to keep this the term on the left. Okay. So to make this the product rule, find the derivative of the first x squared times the second cotangent x squared plus x squared times the derivative of x squared cotangent x squared, or no, not x squared, just cotangent x squared. Okay. Okay. Where are derivatives? Derivatives. This is 2x, that's it, times cotangent x squared. Okay, so that left part was kind of easy, luckily. Plus x squared times, now the chain rule. Okay, what is cotangent x? Whoops. Negative cosecant. Keep tabbing out onto the video. Cosecant squared. Okay, this has to shrink down for sure. This is a lot. Okay. Leave the inside alone. Times the derivative of x squared. Okay, that's not bad, at least. 2x cotangent x squared plus x squared negative cosecant squared x squared times 2x 2x cotangent x squared plus probably 2x cubed negative 2x cubed cosecant squared x squared. Drop the parentheses, 2x cotangent x squared plus, no, minus 2x cubed cosecant squared x squared. Okay, can't do anything with that, but I can put that on the numerator of the entire thing, which I'll rewrite it, fine. 2x cotangent x squared minus 2x cubed cosecant squared x squared all over. Why didn't I distribute that negative 3? There's no reason not to do that, huh? Wait, is this exponent here, is that multiplying this entire term, or? Okay, this is kinda wrong then. This bracket should be on the outside. Wait a minute. Okay, first thing, why is there a bracket? Wait. There should be a bracket here. Okay, so this would be moved out to the front. -4. You can't distribute that 3. You can't. -3. So this bracket should be on the outside, like this. Okay. -3 times 3 plus x squared cotangent x squared to the 4th dy dx. Yeah. And that is that.
Notice one thing, please. I could give this to you with a slightly different look. Check this out. If I gave it to you like this,
Oh, denominator, yeah. Over 1. Be the same thing.
would you verify that that's exactly the same thing? You probably, unless you have a function of x up there, probably shouldn't use quotient rule here. If you use quotient rule with this, it's going to explode in your face. Paper's going to be no! Done. Yeah, it's not going to handle this problem. You need a special paper for that. Okay. They don't sell in stores. No, do this. Okay, unless you have a function of x, because you don't want to deal with that either. If you had a function of x and you move this up top and you're talking about product rule, you can do that, it's fine. But that's just a constant. Move that up for me, would you? And that way you just use a general power rule instead of a quotient rule. Quotient rule would just be ridiculous. So verify that's the same. Then you can start looking at it. So we're going to identify what we're doing on this problem. I need you to see the pieces. What's the biggest piece? General power rule. Very good. General power rule encompasses this whole entire problem. Now let's walk all the way through it. Within the general power rule, after we do that, we're going to come down to these two things, right?
Yeah.
What's the derivative of 3?
0.
That's
0.
great. So we'll be able to do that one nice and easy. How about this piece? What encompasses
Chain rule.
this? Just this. Is it product or chain?
Well, product. Wait. Products, then chain.
Product encompasses the whole thing, doesn't it?
Yeah.
Now within the product rule, I'll take a derivative of x squared. That's easy, 2x. And then I'll have to take a derivative of this little piece right here. What is
Chain
this
rule.
little piece? That's a chain rule. So we're doing general power rule. We will have a product
Rule,
within
then
that.
chain rule.
We'll have a chain rule within that. Okay? It's nice to think about those things though. Nice to think of it as kind of like a graphic organizer or an organizer for advanced organizer for your thoughts. Ready?
Yeah. Woo! Maybe stuff 2 more after that.
Yeah, but they're easier. Sort of. Yeah, sort of. Let's get to it. Come on, you tell me what to do. What am I going to do now?
Negative 3 out front.
Keep everything the same.
Good. Keep everything the same.
So, okay. Now minus 1.
Multiply by the inside.
Yeah,
The
negative 2,
derivative
right?
of the inside.
No.
You know how many mistakes I saw in your homework with that?
Negative
Be
4.
careful. I mean, it would be so sucky if you knew how to do this stuff and you gave me a negative 2 here, right? That would suck. Because I'm like, oh, you know what you're doing. Gone. No, don't do that. Negative 4. Okay, negative 4. Subtract 1 from that. And then what now?
Now we have to multiply it by the derivative of the inside.
Write that out. Go for the derivative inside right now. When we say the inside, we mean the entire expression that you basically ignored. So you should have that on your paper. Do you have that on your paper?
Yeah.
Okay, then you're going to split it up by
Here,
addition.
you're done with that. We're just working on this piece over here. Let's take the derivative of this piece over here. So this is negative 3. X squared cotangent x squared. All right. Negative 4. You're done with that piece times. Probably want a bracket. You need a bracket. Big bracket. Yeah, a lot of stuff. Big bracket. Why big bracket? Well, let's look at that. Derivative of 3.
0.
Oh, that's nice. That's a nice one. If it was just another expression, we could have taken a simple derivative just like we did right here. Right there. So no problem. This is 0. I'm not even going to write the 0. Derivative of 3 is 0. It's constant. Let's focus on this one. You said what
Product
happens
rule.
here? Which is why we need a bracket, because, oh, I'm sorry, no. Product rule. Which is why we need a bracket, because we're going to have an addition in there. Product means plus. You follow? So we need that bracket to organize that. This says, okay, I'm going to have 3's gone, that was a 0. So this goes to 0. This says the derivative of the first times the second. Are you seeing how all our rules are coming back to haunt us? Or help us, however you want to look at it. Plus or minus, folks? Plus what? Finish this off.
X squared
You gotta say it.
times the derivative of cotangent x squared.
Derivative of cotangent x squared.
Cotangent x squared.
Okay, so I'm gonna do x squared first. That's how I like to do it. Derivative of cotangent x squared. Finish off your bracket. Okay, quick head nod if you can follow that. Yes? Okay, cool. Follow our ddx's. Here, no ddx's. Here, ddx. Here, ddx. Negative 3. 3 plus x squared cotangent x squared to the negative 4 power. Big bracket. Derivative of x squared, everybody, what is that?
2x.
Oh, that's nice. 2x cotangent x squared. Well, we got that done. Plus, I don't take the derivative of this x squared. I simply follow my ddx x squared. Tell me what happens here, please. What happens here? What happens?
Chain rule.
For sure, that's a chain rule. Do you guys see the chain rule? Absolutely chain rule. We predicted it right. We had general power rule, product rule, chain rule.
Secant
So we had that
squared.
right.
X
Let's go ahead,
squared
let's do
times the
follow
derivative
dx, do that
of-
chain rule. Chain rule says, here I'm probably going to have at least a parentheses to organize my thoughts a little bit. You don't necessarily need it here because it's just a chain rule. You're not adding or subtracting, but it's kind of nice to have. What happens with that? What's the derivative of cotangent?
Cosecant squared.
Is it?
Cotangent.
Make sure.
Negative cosecant squared.
Negative cosecant squared.
Negative. Wait, did I get that negative? Okay, good. I did. Jeez.
So I'd like it in parentheses just because I know it's a
Scared me.
negative. I don't want to misconstrue that as a minus sign. That's the only reason I have it here. So negative cosecant squared of what, folks? Of what? 2x or x squared?
X squared.
Good. And then we're done, right?
No.
Oh,
Times the
there's one
derivative
thing.
of x
Forget
squared.
this. Oh, it blows our whole problem up. But if we don't forget it, we have the problem right. Times what?
2x.
Yeah. I want ddx of x squared.
2x.
This is this parentheses. That's the bracket.
We didn't have 5 problems on our test.
I can give you one. I can give you one problem, and it would show you everything. Seriously, I could. I'm not gonna. Because if you got it wrong, oh, that sucks. Here goes 20% of your grade. Ha 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 ha, suckers. No, I wouldn't do that to you. I might do that to you if I was retiring. Just don't care anymore. Forget you guys. No, I wouldn't do that. That'd be worse than kicking a puppy. No, about the same level. It's kicking a puppy. Okay, so
Kick the puppy.
general power. Derivative.
I kicked the puppy for you.
Derivative of the inside. Product rule. No problem. Chain rule. We got it. Derivative of the inside right here. That's going to give you 2x and we're done with the calculus. Oops. Last step is just to organize this little piece over here, and then we're good. We're fine. Also, if you wanted to write this on the denominator of a fraction, you could do that. I'll show that to you as well. So we have -3, all this junk. This over here, since we have all being multiplied together, that's a negative, that's a 2x, and that's an x squared.
Minus
A
x
negative,
squared.
a 2x, and an x squared. Tell me what I write. Good.
Is it cube? Oh wait, it is cubes. Did I put that? Yeah. Negative 2x cubed, okay.
Again, if you really wanted to get fancy, you could factor out a 2x here and a 2x here. You could do that if you wanted to. You could distribute the 3 across this, but
Yeah.
not that because the exponent.
But like,
So one
why
last thing
the-
you might
It's
you might
not-
write
It's not fun.
could be all this stuff.
There's no way he's gonna get 2 more examples out of this. Maybe one small one. It's 4 minutes left in the video.
Times the -3. That does not move. It's not associated with that negative exponent.
Unless the one is really easy.
All over that.
Would we be good with just one before it?
Most cases, yeah. Actually, it depends on how I gave it to you. If I gave it to you like that with that negative exponent like I originally did,
Then we'd be good.
that's fine, right? If I gave it to you like 1 over that, I probably would expect you to go back to that. So you see the pattern in it. Because if you see the pattern in it, you can kind of guesstimate what these derivatives will at least look like. Because remember how this was 1 over this to the 3rd? And now it's some crap over this to the 4th? That 4th power, and that doesn't come from nowhere, and that's still right there. Just you have all this junk associated with it. How many people feel okay with what we talked about so far? All right, we start one more. We won't get all the way through it.
I have a question.
Yeah.
You factor out the 2x right there?
Yes, yeah, I was saying that. You could factor out the 2x. This would become negative 6x. This would be cotangent x squared. This would be minus x squared, cosecant squared x squared.
Okay.
And you could do that. If you want to get fancy, you know.
I'm just trying to survive
All right. Two more. Maybe we'll just, you know what? We'll just talk about them. I think you've had enough. This is good enough. I'll put them on the board. We'll talk about what they are, and then you can do them on your own. If you want answers to them, maybe I'll work them out and give you answers at the very end of this thing, just so you can see it on the board. But for right now, here's the problems I'll be doing, and then I want to see if you can do them on your own.
Yeah, not today. Or tomorrow. Okay, probably quotient rule. Split it up by addition and subtraction. Find the derivative of 1, 0. Use the chain rule for cos and sine.
Just kidding.
What?
It's,
No.
do you see how horrible that would be?
Yeah.
You could do it though, couldn't you? Couldn't you?
General power.
General power rule.
Product.
No.
Quotient rule.
Quotient rule.
Quotient rule. Chain
Chain
rules.
rule.
Okay, that would be that.
Plurals. Twice in there.
What's this one? What's this one? Quotient rule comes first. Yes, for sure, because that encompasses the whole problem. Within the quotient rule, do you see the chain rules? If you forget that that's going to have a 2x associated, and it's going to have a 2x associated, that's going to affect your problem. So this is quotient rule, you write quotient rule first. You work it piece by piece, you do the chain rule for each little piece that you come across, and then you're done. Oh, all over the bottom square. Remember that?
Yeah.
I'm going to work this out for you after class, and I'll have this on the video if you want to check your answer. Try that one and see it. So I will work that out for you. The other one is this one. I told you they were going to get a little easier. A little easier. What's this
Product rule and chain rule. That's it.
one? Because I've given this on a test before, and I have people giving this all day long. 2x cosine 3.
What?
I go, I kill you. I kill you.
It's crazy.
Product
Yeah,
rule. Chain rule.
not that.
Product rule. Chain rule.
Product rule first, chain rule within that. Do you see it? And you can handle that one. Okay, we're going to stop there. I'm going to work those out. I'll have them posted in just a little while. Okay, so here we go. Hang on just a second. So we have quotient rule,
Yeah, I was not gonna do this.
chain rule here,
I think I get the point.
chain rule here, derivative of a little piece, derivative of a little piece. The rest is just simplification. This one, here's the answer. So I'll get out of the way, pause the video, and then look at it.
Crikey.
That's fine. Okay.
So today, you're going to learn something called
Implicit differentiation. I've heard of this yesterday. What was it from? Dude, I remember seeing this yesterday. I don't know why. Differentiate each side of an equation with two variables. Oh, I know. I was looking up a problem on Photomath, and it used implicit differentiation, I'm pretty sure. We differentiate each side of an equation with two variables by treating one of the variables as a function of the other. Okay. That sounds kind of cool, actually. We've been doing it this whole time. Mind blown. Thanks, Professor Leonard. Professor Leonard, I go to a huge university. It's nice to have a teacher teach a small class. You answer the questions I have without me asking them. Is this like, I didn't watch video, obviously. Is this like that time whenever he's, like, you were doing derivatives the whole time or something? Because that'd be pretty cool. So we got an hour-long video tomorrow. 53 minutes, another hour and a half. It's gonna suck. A 6-minute, a 26-minute, a 36-minute. Those 3 days are gonna be nice. If I'm feeling extra try hard though, I might combine them. That would save a lot of time actually, wouldn't it? I might do that. That's very try hard though. Hour and a half, hour and a half, hour and a half. 3 hours is gonna suck. Hour and a half, 2 hours also gonna suck. Half an hour, 3 hours, hour and a half, 3 hours, hour, 2 hours. Okay, I think an hour is like good. Anything above that, it gets kinda 3 hours is gonna really suck. It's only like 3 of them though. What do we get in the integrals, so? Chapter 4, I think. What's chapter 3? Increasing and decreasing, increasing/decreasing concavity of functions. Concavity? Cavity? Chapter 3 looks really short compared to the others. Actually, no, never mind, it's not. It's really not. How did I drag this out of 3 hours 15 minutes? That's crazy. Alright, tomorrow implicit differentiation. Let's go.